Right now, 10 billion years of cosmic theory is collapsing. The James Webb Space Telescope has found something that should not exist. 10 galaxies. Impossible galaxies. Monsters that formed when the universe was barely 400 million years old. Back when space itself was still molten. Back when the first stars were just learning to burn. These galaxies are not young. They are not small. They are titans. Each one contains as many stars as the Milky Way contains today. Hundreds of billions of suns packed into structures that had no right to exist for another billion years. And they are everywhere Webb looks. This is not a measurement error. This is not a calibration glitch. 6 independent teams have confirmed it. The galaxies are real. The dates are real. And every model we built to explain how galaxies form, how matter clumps together, how dark matter shepherds visible matter into stars, every equation that took 40 years to perfect is breaking. Something is accelerating structure formation in the early universe, something we did not account for, something that does not care about the laws we wrote. The universe was not supposed to wake up this fast. Let me tell you what Webb actually photographed. The year was 2022. The telescope had been in space for less than 6 months. NASA pointed it at a patch of sky smaller than a grain of sand held at arm's length. A region called SMACS 0723. They expected to see infant galaxies. Smudges of light. Primitive clumps of hydrogen gas just beginning to collapse under their own weight. Instead, Webb found empires. Galaxy after galaxy blazing with impossible brightness. Not the faint red whispers of newborn stars struggling to ignite. These were mature stellar populations. Ancient light. Red giants and white dwarfs mixed together in a way that should take billions of years to achieve. The spectrum did not lie. These galaxies had been cooking stars for hundreds of millions of years already. But the universe itself was only 400 million years old. Do the math. If these galaxies had been forming stars for hundreds of millions of years, they must have started assembling almost immediately after the Big Bang. There was no grace period, no slow buildup. The universe went from smooth plasma to galactic supercities in a geological eye blink. Astrophysicist Ivo Labbé from the Swinburne University of Technology in Australia led one of the analysis teams. He called them universe breakers, not as a joke, as a diagnosis. These galaxies break every timeline we constructed. They shatter the standard model of cosmology. Here is what you need to understand about how galaxies are supposed to form. In the beginning, the universe was perfectly smooth. No clumps, no structure, just a hot fog of hydrogen and helium expanding outward from the Big Bang. Temperature, 3000 degrees Kelvin. Density, uniform to 1 part in 100,000, a cosmic ocean with no islands. Then gravity started to work. Wherever the density was even slightly higher, by a fraction of a percent, gravity pulled harder. More matter fell in. The dense regions got denser. The voids got emptier. Over millions of years, this process carved the cosmic web, filaments of dark matter stretching across billions of light years. Galaxies forming where the filaments intersected like dewdrops on a spider's silk. But this process is slow, agonizingly slow. Dark matter does not interact with light. It does not feel electromagnetic force. It only responds to gravity. And gravity at cosmic scales is a patient predator. It does not pounce. It coils. It tightens over epochs. The first stars were not supposed to form until 150 million years after the Big Bang. Small stars, metal-free, burning pure hydrogen in cores the size of Jupiter. These population 3 stars lived fast and died young, exploding as supernovae, seeding space with carbon and oxygen and iron. Only then, after the first generation of stars died, could the second generation begin. Stars with planets, stars with chemistry, stars that could anchor galaxies. The timeline is strict. First stars at 150 million years. First small galaxies at 500 million years. Large galaxies like the Milky Way not until 1 billion years or later. Webb just found fully assembled galaxies at 350 million years. These are not first-generation galaxies, they are third generation. Fourth generation, they contain stars that have already lived and died. Supernova remnants. Heavy elements. Dust. The spectroscopic signature is unmistakable, which means these galaxies started forming much earlier, possibly at 100 million years, possibly earlier. The universe did not wait. Astronomer Dan Coe from the Space Telescope Science Institute in Baltimore examined one galaxy in particular. Designation Glass Z13. Redshift 13.1. That redshift translates to a look-back time of 13.4 billion years. The universe was 300 million years old when that light was emitted. Glass Z13 is not a dwarf galaxy. It is not a proto-galaxy. It contains roughly 1 billion solar masses of stars. That is 1 billion times the mass of our Sun, all packed into a region smaller than the Large Magellanic Cloud. Here is the problem. To build a galaxy containing 1 billion solar masses of stars in 300 million years, you need to form stars at a rate of roughly 3 solar masses per year. Every single year, for 300 million years. No breaks, no pauses, no periods of dormancy. The Milky Way today forms stars at a rate of approximately 1.5 solar masses per year. We are a mature, efficient star factory, and we have been doing this for over 10 billion years. These infant galaxies were forming stars twice as fast as the Milky Way, while the universe was still an infant. While the temperature of the cosmic microwave background was still warm enough to feel, something accelerated the process. Something bypassed the slow gravitational collapse that was supposed to take billions of years. And that something is invisible. Dark matter. Let me explain what dark matter actually is, because most people think it is a theory. It is not. Dark matter is an observed fact. We do not know what it is made of, but we know with absolute certainty that it exists. The proof comes from rotation curves. In the 1930s, astronomer Fritz Zwicky was studying the Coma Cluster, a collection of over 1,000 galaxies located 320 million light-years from Earth. He measured how fast the galaxies were moving relative to each other. Then he used Newton's laws to calculate how much mass the cluster needed to hold itself together gravitationally. The numbers did not match. The galaxies were moving too fast. Far too fast. At the speed Zwicky measured, the cluster should have torn itself apart within a few million years. But the Coma Cluster is billions of years old. It is stable, which means there must be additional mass holding it together, mass we cannot see. Zwicky called it Dunkel Materie, dark matter. For decades, astronomers ignored him. They assumed he made a mistake. Then in the 1970s, astronomer Vera Rubin measured the rotation curves of individual spiral galaxies. She pointed her spectrograph at galaxy after galaxy and measured how fast stars were orbiting the galactic center at different distances. The pattern was wrong. According to Newton's laws, stars far from the galactic center should orbit slowly, just like planets far from the Sun orbit slowly. The gravitational pull weakens with distance. Orbital velocity should drop off, but it does not. Stars at the outer edge of galaxies orbit just as fast as stars near the center. The rotation curve is flat, completely flat, as if the galaxy's mass extends far beyond the visible stars. As if there is a massive halo of invisible matter surrounding the entire galaxy. Rubin measured 60 spiral galaxies. Every single one showed the same flat rotation curve. There is no way to explain this with visible matter alone. The math is ironclad. Either Newton's laws are wrong, or there is 5 times more matter in the universe than we can see. We chose the latter. Today, we know dark matter makes up roughly 85% of all matter in the universe. Visible matter, the atoms that make up stars and planets and you, accounts for only 15%. We are the minority, we are the afterthought. But we still do not know what dark matter is. It is not made of atoms. Atoms interact with light. Dark matter does not. It is not black holes. We would see gravitational lensing. It is not gas or dust. We would detect it in other wavelengths. The leading theory is that dark matter is a new type of subatomic particle, something that only interacts via gravity. Physicists call them WIMPs, weakly interacting massive particles. These particles would have been created in the first microseconds after the Big Bang, flooding the universe in numbers we cannot imagine. 1,000 WIMP particles pass through your body every second. You do not feel them. They do not touch your atoms. They fall through the earth like ghosts through walls. But they have mass, and mass has gravity, and gravity built the galaxies. Here's how galaxies are supposed to form step by step according to the standard model. Step 1. Dark matter clumps first. In the early universe, before atoms even existed, dark matter was already collapsing into halos. These halos acted like gravitational wells, invisible scaffolding waiting for visible matter to arrive. Step 2. Hydrogen gas falls into the dark matter halos. The gas is still hot from the Big Bang, too hot to collapse immediately. It has to cool. Cooling takes time, hundreds of millions of years. Step 3. Once the gas cools enough, it collapses into the center of the dark matter halo. Density increases. Temperature rises. Eventually, nuclear fusion ignites. The first stars are born. Step 4. The stars explode as supernovae. The explosions blow gas out of the galaxy. This is called feedback. It prevents all the gas from turning into stars at once. It regulates star formation, keeps it slow and steady. Step 5. Over billions of years, the galaxy accretes more gas from the cosmic web, merges with smaller galaxies, grows slowly into a spiral or elliptical structure. This process is supposed to take a minimum of 500 million years. Probably longer, probably 1 billion years for a galaxy the size of the Milky Way. Webb found these galaxies at 350 million years. Which means one of 3 things is happening. Option 1. Dark matter clumped faster than we thought. The halos formed earlier, denser, stronger, for reasons we do not understand. Option 2. Gas cooled faster than we thought. There was less feedback than we predicted. Stars formed in a runaway process, turning gas into starlight at a rate we did not think was possible. Option 3. We are completely wrong about how dark matter works. The third option terrifies cosmologists. Cosmology is not like other sciences. In biology, if you discover a new species, you update the taxonomy. You add a branch to the tree of life. The foundation stays intact. In cosmology, everything is connected. Every measurement depends on every other measurement. The age of the universe determines the Hubble constant. The Hubble constant determines dark energy density. Dark energy density determines the fate of the universe. Pull one thread and the entire tapestry unravels. These 10 galaxies are pulling that thread. Let me show you exactly how impossible they are. Galaxy designation CEERS 93516. Discovered in August 2022. Redshift 16.7. That redshift puts it at 250 million years after the Big Bang. The earliest galaxy ever confirmed. But here is what makes it a nightmare. The stellar mass is approximately 100 million solar masses. That means 100 million stars, each roughly the size of our Sun, all packed into a region 500 light-years across. For comparison, the nearest star to our Sun is 4 light-years away. In CEERS 93516, stars are separated by hundredths of a light-year. The night sky on a planet in that galaxy would not have stars. It would be a wall of light. Now calculate the formation timeline. 100 million solar masses, 250 million years. That is a star formation rate of 0.4 solar masses per year, sustained without interruption since almost the moment the universe began. But that is just the average. Star formation does not happen smoothly. It happens in bursts, triggered by shock waves from supernovae. Driven by collisions between gas clouds, a realistic model requires periods where the star formation rate spikes to 10 or 20 solar masses per year. The energy output would be catastrophic. Every star above 8 solar masses explodes as a supernova within 10 million years. These massive stars pump out ultraviolet radiation while they live, heating the surrounding gas. Then they explode, sending shock waves tearing through the galaxy at 10,000 kilometers per second. These shock waves should blow the gas out of the galaxy entirely, should stop star formation dead. This is the feedback mechanism I mentioned earlier. This is what keeps galaxies from burning through all their fuel in one apocalyptic burst. Except it did not happen. CEERS 93516 kept forming stars, kept pulling in gas, kept growing. The supernova feedback that should have regulated the process failed completely. Why? Astrophysicist Tommaso Treu from UCLA led a team analyzing 6 of these impossible galaxies. His conclusion: the dark matter halos must have been significantly denser than current models predict. Let me explain what that means. A dark matter halo is not uniform. It has a density profile. The center is denser than the edges. How dense the center is determines how strongly the halo can hold onto gas against supernova feedback. Current models predict that early dark matter halos had central densities around 10 to the power of -24 grams per cc. That is the density of one hydrogen atom per cc, almost nothing. But if these galaxies exist, the central densities must have been at least 10 times higher. Maybe 100 times higher. Dense enough to trap gas. Dense enough to force it inward against the outward pressure of exploding stars. Why were the halos denser? We do not know. One possibility: the initial density fluctuations in the early universe were larger than we thought. The Big Bang was lumpier, more inhomogeneous. This would cause dark matter to collapse faster, creating denser halos earlier. But there is a problem. We have already measured those initial fluctuations. The Planck satellite mapped the cosmic microwave background with exquisite precision. The fluctuations were 1 part in 100,000. We know this number to 5 decimal places. If the fluctuations were larger, Planck would have seen them. It did not. Another possibility: dark matter is not cold. It is warm. Let me explain the difference. Cold dark matter moves slowly. The particles have low velocities. This allows them to clump on small scales, forming halos around individual galaxies. Warm dark matter moves faster. The particles have higher velocities. This prevents them from clumping on small scales. They smooth out structure. Galaxies form later. Fewer dwarf galaxies exist. For decades, cold dark matter has been the standard model because it matches observations perfectly. The cosmic web. The large-scale structure. The distribution of galaxies. All of it fits cold dark matter predictions. But warm dark matter has one advantage. It can collapse faster on large scales. If dark matter particles have just enough velocity, they can stream into overdense regions faster than cold dark matter, creating denser halos earlier. The problem: warm dark matter predicts fewer small galaxies. We observe thousands of dwarf galaxies orbiting the Milky Way. Warm dark matter says most of them should not exist. Unless the transition happened. Unless dark matter was warm in the early universe and became cold later. A phase transition. A change in the particle properties as the universe cooled. This is not impossible. Particle physics allows for it. But we have never seen evidence for it. Until now. Theoretical physicist Abraham Loeb from Harvard University proposed another explanation. He suggests these are not galaxies at all. They are supermassive black holes surrounded by accretion disks. Here is his logic. In the first 100 million years after the Big Bang, the universe was filled with pristine hydrogen gas. No metals. No carbon or oxygen to cool the gas efficiently. When this metal-free gas collapses, it cannot fragment into small stars. It collapses directly into supermassive objects. These objects could be massive stars, hundreds or thousands of solar masses. They burn bright and fast, living only a few million years before collapsing into black holes. Or the gas could collapse directly into black holes without forming stars at all. Direct collapse black holes. Seeds weighing 100,000 solar masses appearing within the first 100 million years. Once the black hole exists, it starts feeding. Gas spirals inward, forming an accretion disk. The disk heats up from friction, glowing with the light of a billion suns. From a distance, this looks identical to a galaxy. Webb cannot tell the difference. The light is the same, the redshift is the same. The only way to distinguish a galaxy from a supermassive black hole is with spectroscopy. You need to see the individual stellar absorption lines. Webb has not yet obtained high-resolution spectra for all 10 candidates. If Loeb is right, these are not impossible galaxies, they are impossible black holes. Which is arguably worse. Because black holes this massive should not exist either. Galaxy designation: JADES GSZ 130. Discovered November 2022. Redshift 13.2. Age: 320 million years after the Big Bang. This one is different. The spectrum shows clear evidence of oxygen. Not just hydrogen and helium, oxygen. That means stars have already lived and died. Supernovae have already exploded. The galaxy has been chemically enriched. Oxygen is created inside massive stars through nuclear fusion. Carbon and oxygen fuse into heavier elements in the final stages of stellar evolution. When the star explodes, it scatters oxygen across space. This process takes time. A massive star needs at least 3 million years to evolve from birth to supernova. Then you need another generation of stars to form from the enriched gas. Then, those stars need to produce light visible across billions of light years. JADES GSZ 130 has oxygen, which means at least 2 generations of stars have already lived and died. Which means the galaxy is at least 10 million years old. Probably older. probably 50 million years old. But the universe itself is only 320 million years old when we see this light. Subtract 50 million years. That means the galaxy started forming at 270 million years. 270 million years after the Big Bang, the cosmic microwave background radiation had a temperature of 60 Kelvin. That is minus 213 degrees Celsius, cold enough to freeze nitrogen. The universe was still cooling from the Big Bang. And in that frozen darkness, this galaxy was already burning. Here is what cosmologist Michael Boylan-Colchin from the University of Texas calculated. To produce the stellar populations we see in these 10 galaxies, dark matter halos need to be more efficient at turning gas into stars than any galaxy in the modern universe. The efficiency is measured by a number called the stellar-to-halo mass ratio. It is exactly what it sounds like: the mass of stars divided by the mass of the dark matter halo. In the modern universe, this ratio peaks at about 2%. That means for every 100 solar masses of dark matter, the halo produces 2 solar masses of stars. This is the maximum efficiency ever observed. More than 2% is impossible because supernova feedback blows away the remaining gas. These Webb galaxies have ratios between 5 and 10%. 10% efficiency means the halo converts gas into stars 5 times more effectively than the Milky Way, 5 times more effectively than any galaxy in the observable universe today. Boylan-Colchin calls this the impossible early galaxy problem. It is not that the galaxies are large, it is that they are too efficient. The star formation happened too fast, too completely, too perfectly. Something overrode the feedback mechanisms. Something suppressed the supernova-driven winds that should have shut down star formation. What could do that? One option: magnetic fields. Strong magnetic fields can confine gas, preventing it from escaping the galaxy even when supernovae explode. The magnetic pressure counteracts the thermal pressure of the hot gas. But magnetic fields this strong should not exist in the early universe. Magnetic fields are generated by rotating plasmas, by dynamos inside stars, by accretion disks around black holes. All of these processes take time. At 300 million years, there has not been enough time to build galactic-scale magnetic fields strong enough to trap supernova ejecta. Another option, the initial mass function, was different. The initial mass function describes the distribution of stellar masses when stars form. In the modern universe, most stars are small, red dwarfs below half a solar mass. Only a tiny fraction are massive stars above 8 solar masses. This is important because massive stars are the ones that explode as supernovae. If fewer massive stars form, there is less feedback, less disruption. More gas remains in the galaxy to form additional stars. But if the initial mass function was different in the early universe, if more low-mass stars formed and fewer high-mass stars, then supernova feedback would be weaker. Star formation could continue uninterrupted. Why would the initial mass function be different? Temperature. Gas temperature determines how it fragments when it collapses. Cold gas fragments into small pieces, forming small stars. Hot gas fragments into large pieces, forming massive stars. In the early universe, gas was hotter. The cosmic microwave background radiation had not yet cooled to its current temperature of 3 Kelvin. At redshift 10, the CMB was 30 Kelvin. That is warm enough to heat gas clouds, preventing them from fragmenting into small pieces. So the initial mass function should favor massive stars in the early universe, not small stars, which makes the problem worse, not better. We are running out of solutions. There is one more option. One that physicists do not like talking about because it opens a door we spent 50 years trying to seal shut. What if dark matter interacts with itself? Standard dark matter theory assumes dark matter particles never interact with each other. They pass through each other like ghosts. The only force they feel is gravity. This is called collisionless dark matter. Every simulation we have run for 40 years assumes this. The Millennium Simulation, the Illustris Project, the Eagle Simulation. Supercomputers running for months, tracking billions of dark matter particles as they collapse under gravity, forming the cosmic web. All of them assume dark matter is collisionless. And all of them predict galaxies should form slowly. But what if dark matter particles do interact? Not through electromagnetism, not through the strong nuclear force, through something else. A new force we have never detected. A dark force that only affects dark matter. If dark matter particles can collide with each other, everything changes. When normal matter collides, it loses energy. Gas clouds crash together, heat up, radiate energy as light, and cool down. This allows them to collapse further. This is how stars form. Dark matter cannot radiate light. But if dark matter particles can collide, they can transfer momentum. They can scatter, and scattering causes friction. Friction causes dissipation. Dissipation allows collapse. Self-interacting dark matter would clump faster than collisionless dark matter. The halos would be denser at the center. Gas falling into these halos would be compressed more strongly. Star formation would ignite earlier. Galaxies would assemble in half the time. This could explain the Webb galaxies. But there is a cost. Self-interacting dark matter solves one problem and creates 10 others. It predicts that the cores of dark matter halos should be less dense than observations show. It predicts that galaxy clusters should have rounder shapes than we observe. It predicts effects we have never seen, unless the interaction strength is tuned precisely. Unless the cross-section is exactly right. Not too strong, not too weak. Strong enough to accelerate early galaxy formation. Weak enough to avoid detection in the modern universe. Physicist Haibo Yu from the University of California, Riverside has spent a decade modeling self-interacting dark matter. His team published a paper in January 2023 analyzing whether it could explain the Webb observations. The answer: maybe. If the cross-section per unit mass is around 0.1 to 1 square centimeter per gram, if the interaction is velocity-dependent, if it was stronger in the early universe when dark matter particles were moving faster, these are not unreasonable numbers, but they require inventing a new particle, a new force, a new interaction term in the standard model of particle physics. Occam's razor says the simplest explanation is usually correct. Adding new particles and forces is not simple, but the alternative is worse. The alternative is admitting we do not understand how galaxies form, that the past 40 years of cosmological simulations are built on wrong assumptions. That dark matter is not what we thought it was. Galaxy designation, Glass Z10. Redshift, 10.0. Age, 480 million years after the Big Bang. This galaxy breaks a different rule. The morphology is wrong. Morphology means shape. Glass Z10 is not a blob. It is not an irregular clump of stars like we expect from early galaxies. It is a disk, a rotating disk with spiral structure. Spiral galaxies take time to form. You need rotation. You need angular momentum conservation. You need the gas to settle into a stable disk configuration where stars orbit in circular paths around a central bulge. This process is supposed to take billions of years. The Milky Way did not develop its spiral structure until it was at least 3 billion years old. Before that, it was a chaotic mess. Dwarf galaxies merging, gas clouds colliding, stars flying in random orbits. Glass Z10 has spiral arms at 480 million years. Astrophysicist Catherine Whittaker from the University of Massachusetts analyzed the light profile. The brightness distribution follows an exponential disk, the same profile seen in modern spiral galaxies like M31 or NGC 6308. How did it form so fast? Disks require cold gas, gas that has lost its random thermal motion and settled into orderly rotation. In the modern universe, this happens through a process called cooling flow. Hot gas in the halo radiates energy and spirals inward, losing energy until it settles into a disk. Cooling time depends on density. High-density gas cools faster. Low-density gas cools slowly. At 480 million years, the universe was denser than today. The average density was about 1,000 times higher. This should accelerate cooling, but not by a factor of 10. Not enough to form disks in a few hundred million years, unless the gas was never hot to begin with. Standard theory says gas heats up when it falls into dark matter halos. Gravitational potential energy converts into kinetic energy. The gas compresses and heats up, reaching temperatures of 1,000,000 Kelvin or more. But what if it did not heat up? What if the gas fell in cold? This is called cold mode accretion. It happens when gas flows into halos along narrow filaments of the cosmic web. The filaments are dense enough that the gas cools as fast as it heats. It stays cold all the way down, settling directly into a disk without passing through a hot phase. Cold mode accretion is supposed to dominate in the early universe, but simulations predict it only works for halos below a certain mass. Above 10 to the power of 12 solar masses, the gas always shocks and heats. Glass Z10's halo mass is estimated at 2 times 10 to the power of 11 solar masses. Below the threshold, cold mode accretion should work, except the disk is too perfect, too smooth, too well ordered. Real cold flows are turbulent, chaotic. They produce lumpy, irregular disks with large amounts of vertical thickness. Glass Z10's disk is thin. The scale height is less than 500 parsecs. That is thinner than the Milky Way's disk. For reference, 1 parsec equals 3.26 light-years. A thin disk requires more than cold flows. It requires time. It requires the random motions to damp out through repeated star formation and feedback cycles. It requires settling. We are back to the same problem. Everything is happening too fast. Astronomer Erica Nelson from the University of Colorado identified another anomaly. The stellar populations in Glass Z10 show evidence of multiple ages. The central bulge contains older stars, red giants and white dwarfs. The spiral arms contain young blue stars. This age gradient is exactly what we see in modern spirals. It indicates the galaxy has been forming stars for a long time, long enough for different regions to have different star formation histories. But the galaxy is only 480 million years old. How long is a long time in that context? At least 200 million years. Maybe 300 million, which means Glass Z10 started forming stars at 150 million years after the Big Bang, during the Dark Ages. Before the first stars were supposed to exist. The Dark Ages. Let me explain what that means. Immediately after the Big Bang, the universe was opaque, filled with ionized plasma. Photons could not travel freely. They scattered off electrons constantly, like light in thick fog. 380,000 years after the Big Bang, the universe cooled enough for electrons to combine with protons, forming neutral hydrogen. This event is called a recombination. Suddenly, photons could travel freely. The universe became transparent, but there were no stars yet, no light sources. The universe was filled with neutral hydrogen gas floating in darkness. This period is called the Cosmic Dark Ages. The Dark Ages lasted from 380,000 years to 150 million years. During this time, gravity slowly pulled the gas into dense regions. Dark matter halos grew. Gas collapsed. Eventually, the first stars ignited, ending the Dark Ages. This transition is called the Epoch of Reionization. The first stars produced ultraviolet radiation powerful enough to ionize hydrogen. The ionized bubbles expanded, merging with each other, until the entire universe was ionized again. Webb was specifically designed to observe the epoch of reionization, to see the first stars turning on, to watch the Dark Ages end. Instead, Webb found galaxies that were already mature when the Dark Ages ended. Galaxies with hundreds of millions of years of star formation history behind them. Galaxies that somehow assembled in the dark, before light existed. How do you form a galaxy in the dark? You cannot see, you cannot radiate away energy as light. The only force available is gravity, and gravity alone does not work fast enough, unless dark matter is doing something we did not predict. Physicist Dan Hooper from Fermilab proposed a radical idea in February 2023. He suggests dark matter might decay. Here is the concept. Dark matter particles are not stable. They have a finite lifetime. After a certain period, they decay into lighter particles, releasing energy in the process. In the modern universe, this decay would be undetectable. The dark matter we see around us is 13.8 billion years old. If the decay lifetime is longer than the age of the universe, most particles have not decayed yet. But in the early universe, things were different. The dark matter particles were freshly created, just born in the Big Bang. If even a small fraction of them decayed in the first few 100 million years, they would release energy. That energy could heat the gas, could compress it, could trigger star formation earlier than gravity alone would allow. The amount of energy does not need to be large. Just 1% of the dark matter mass decaying into kinetic energy would be enough to collapse gas clouds 1,000,000 times faster than normal. This is elegant. This is testable. If dark matter decays, it should produce specific particle signatures. Gamma rays, neutrinos, positrons. Experiments like the Fermi Gamma Ray Space Telescope and the Alpha Magnetic Spectrometer on the International Space Station are searching for these signals. So far, nothing. No excess gamma rays, no anomalous positrons, no evidence of dark matter decay. But the limits are weak. We can only rule out decay rates above a certain threshold. Below that threshold, the signal is too faint to detect. Hooper calculates that a decay lifetime of 1 billion years would explain the Webb observations without producing detectable signals in modern experiments. 1 billion years. Long enough to avoid detection today, short enough to flood the early universe with energy. But there is a philosophical problem. If dark matter decays, then what we see today is not the same dark matter that existed in the early universe. The early dark matter is gone, decayed into something else. The current dark matter is a different population, younger particles that have not yet decayed. This means the properties of dark matter change over time. The universe we study today is not the same universe that existed at redshift 10. The rules were different then. Cosmologists hate this. Cosmology is built on the assumption that physical laws are constant. The speed of light does not change. The gravitational constant does not change. Dark matter does not change. If dark matter evolves, then every simulation is wrong. Every prediction is invalid. We would need to rebuild cosmology from the ground up. Galaxy designation: JADES GSZ14. Redshift 14.32. Age 280 million years after the Big Bang. This is the current record holder, the most distant galaxy ever confirmed. But here is what makes it terrifying. It is not alone. When the JADES team pointed Webb at the same patch of sky for 3 weeks, they found 8 galaxies at redshift greater than 12. 8. In one tiny region of space. The volume they surveyed is roughly 100 cubic megaparsecs. 1 megaparsec equals 3.26 million light-years. So they searched a box roughly 300 million light-years on a side. 8 bright galaxies in that volume at redshift 12 translates to a number density of approximately 8 times 10 to the power of -5 galaxies per cubic megaparsec. Compare this to predictions. The standard cold dark matter model predicts a number density of approximately 1 times 10 to the power of -6 galaxies per cubic megaparsec at redshift 12. The observations exceed predictions by a factor of 80. 80 times more galaxies than should exist. This is not a small discrepancy. This is not a factor of 2 or 3 that could be explained by measurement uncertainties or selection effects. This is a factor of 80. Nearly 2 orders of magnitude. Either Webb happened to point at the single most overdense region in the entire observable universe, or the models are catastrophically wrong. Cosmologist Ivo Labbé calculated the probability. If the standard model is correct, the odds of finding 8 bright galaxies in a random survey volume at redshift 12 is approximately 1 in 10,000. 1 in 10,000. Possible, but unlikely. But Webb did not perform one survey. Multiple teams have surveyed different fields. The CEERS survey, the GLASS survey, the SMACS survey. All of them find similar densities. All of them find too many bright galaxies. The probability of all surveys randomly pointing at overdense regions is 1 in 10,000 raised to the power of the number of surveys. That is 1 in trillions. We can rule out cosmic variance. These galaxies are not rare fluctuations. They are common, which means the universe was assembling structure much faster than we calculated. Astronomer Stephen Finkelstein from the University of Texas leads the CEERS collaboration. In March 2023, he published an analysis showing that the stellar mass density at redshift 12 is approximately 50% of the stellar mass density at redshift 8. Read that again. Half of all the stars that existed 400 million years were already formed by 300 million years. Star formation did not ramp up gradually. It exploded. The first 100 million years produced as many stars as the next 300 million years. This is called a burst mode of star formation. It is the opposite of the steady, regulated process we observe in the modern universe. Why did it stop? Why did star formation slow down after the initial burst? One possibility: the gas ran out. The initial burst converted all available gas into stars, leaving nothing for future generations. But this does not match observations. Galaxies at redshift 8 still have gas. They are still forming stars. The gas did not run out. Another possibility: feedback finally kicked in. After enough supernovae exploded, the cumulative effect finally became strong enough to blow gas out of the galaxy. But why did it take so long? Why did feedback fail during the first burst and only succeed later? A third possibility: reionization. When the first galaxies turned on, their ultraviolet radiation ionized the hydrogen gas in the surrounding intergalactic medium. Ionized gas is hot. Hot gas cannot collapse into new galaxies easily, Reionization would act like a cosmic thermostat. It would heat the gas reservoirs, feeding the first galaxies, cutting off their fuel supply. Star formation would slow down not because of internal feedback, but because of external radiation from other galaxies. This explanation is appealing. It explains why star formation slowed down across the entire universe at the same time. It is not a coincidence. It is a phase transition. But it requires reionization to happen early, before redshift 12, before 300 million years. Previous observations suggested reionization happened later. Around redshift 6 to 8, between 500 million and 1 billion years. Webb is rewriting that timeline. If these bright galaxies exist at redshift 14, they are producing enough ultraviolet radiation to ionize the universe much earlier than we thought. Reionization is not a gentle process. It is violent. When ultraviolet photons hit neutral hydrogen atoms, they rip the electron away from the proton. The atom ionizes. The freed electron carries kinetic energy. It collides with other atoms, ionizing them. A chain reaction begins. Inside a galaxy, this is controlled. Stars produce UV radiation steadily. The gas around them ionizes gradually, forming H2 regions. These ionized bubbles expand slowly, giving gas time to adjust. But in the intergalactic medium, reionization is a shock wave. Imagine a galaxy turning on in the Dark Ages. Suddenly, a sphere of ionized hydrogen expands outward at the speed of light. The ionization front is a wall, a boundary between neutral and ionized gas. And that boundary is moving at 300,000 kilometers per second. Gas ahead of the front is cold, 10 Kelvin. Gas behind the front is hot, 10,000 Kelvin. That is a 1,000-fold temperature increase in the time it takes light to cross an atom. The pressure difference is catastrophic. The hot gas expands violently, driving a shock wave into the cold gas. The shock compresses the neutral gas, heating it, potentially triggering runaway collapse. Simulations by cosmologist Nikolay Ganedin from Fermilab show that reionization affects different mass halos differently. Small halos, below 1 million solar masses, lose all their gas. The hot ionized gas escapes their gravitational wells completely. These halos can never form stars. This is called photoevaporation. The radiation evaporates the gas reservoir like sunlight evaporating a puddle. Medium-sized halos between 1 million and 10 million solar masses lose some gas but retain enough to continue forming stars at a reduced rate. Large halos above 100 million solar masses are barely affected. Their gravity is strong enough to hold on to gas even when it is heated. The Webb galaxies are all in the large halo category. They should survive reionization easily. But here is the problem. If reionization happened as early as redshift 14, then there are no small halos anymore. Every halo below 1 million solar masses was sterilized. Their gas was blown away. They became dark galaxies. Halos containing dark matter but no stars. Dark galaxies should be everywhere. Thousands of them orbiting every large galaxy like invisible satellites. We have searched for them. We have looked for gravitational lensing effects. For kinematic signatures in hydrogen gas, we have found a few dozen, not thousands, dozens. Either reionization did not happen as early as Webb suggests, or dark galaxies do not exist in the numbers predicted. Both options are bad. Astronomer Brant Robertson from UC Santa Cruz published a paper in April 2023 analyzing the reionization timeline implied by Webb observations. His conclusion: the universe was 50% ionized by redshift 10, fully ionized by redshift 6, That matches previous observations. That is the orthodox timeline. But Robertson also points out a contradiction. If bright galaxies exist at redshift 14, they are producing copious amounts of UV radiation. That radiation should ionize the surrounding intergalactic medium locally. We should see ionized bubbles at redshift 14. Webb has not seen them. The spectroscopy shows neutral hydrogen persisting between galaxies, even at redshift 12. The galaxies are bright. The intergalactic medium is neutral. These two facts do not fit together. Unless the UV radiation is not escaping the galaxies, unless something is absorbing it before it reaches the intergalactic medium, what could absorb ultraviolet light? Dust. Dust is made of tiny grains: carbon, silicon, iron. These grains are typically 100 nanometers across. They form in the atmospheres of dying stars. Red giants and supernovae eject dust into space. Dust absorbs ultraviolet light and re-emits it as infrared. This is why dusty galaxies appear red. The blue light is absorbed. Only red and infrared light escapes. If these early galaxies contain significant amounts of dust, their UV radiation would never reach the intergalactic medium. The photons would be absorbed and reprocessed before they could ionize anything. But dust requires heavy elements: carbon, silicon, oxygen. These elements are not created in the Big Bang. They are synthesized inside stars and expelled during supernovae. Building up significant dust content takes time. It requires multiple generations of stars, hundreds of millions of years of stellar evolution. At redshift 14, there has not been enough time. The universe is 280 million years old. That is barely enough time for one generation of massive stars to form and explode. Yet spectroscopy of some Webb galaxies shows dust signatures, absorption features indicating carbon and silicon grains. Galaxy designation: A2744YD4, redshift 8.4, age 600 million years. This galaxy is not as distant as the record holders, but it is significant for a different reason. The infrared spectrum shows a pronounced dust continuum. The light is heavily reddened. Calculations suggest a dust mass of approximately 10 million solar masses. 10 million solar masses of dust. At 600 million years after the Big Bang, to produce that much dust, you need approximately 100 million solar masses of stars to live, evolve, and die as supernovae. Each supernova produces roughly one solar mass of dust, 100 million solar masses of stars. At an average stellar mass of one solar mass, that is 100 million individual stars. All formed, all evolved, to the end of their lives, all exploded. The lifetime of a massive star is approximately 3 million years for a star 20 times the mass of the Sun. Smaller stars live longer. Even assuming all stars were massive and short-lived, you need at least 3 million years of continuous star formation to build the stellar population. Then 3 million years for them to die. That is 6 million years minimum. But realistically, most stars are not massive. Most stars are low mass. The median stellar lifetime is probably 10 million years, which means the star formation must have started at least 10 million years before the observation time. 600 million minus 10 million equals 590 million years. The galaxy started forming stars at 590 million years after the Big Bang. That is plausible. That fits the standard timeline. But here is the issue. The dust mass is too high for a single generation of stars. If 100 million solar masses of stars exploded, producing one solar mass of dust each, you get 100 million solar masses of dust. But A2744YD4 only has 10 million solar masses of dust. Where did the other 90 million solar masses go? Some dust is destroyed. Supernova shockwaves can vaporize dust grains. Collisions between grains can shatter them into atoms. Ultraviolet radiation can break molecular bonds. But these processes are not efficient enough to destroy 90% of the dust. Typical destruction efficiencies are 10 to 20%, not 90%. The only way to reconcile the numbers is if dust formation is less efficient than we thought. If supernovae produce less than one solar mass of dust each. Recent observations of nearby supernovae support this. The Crab Nebula, the remnant of a supernova that exploded in the year 1054 AD, contains only 0.1 solar masses of dust. Not one solar mass, 10 times less. If supernova dust yields are 10 times lower than assumed, then the stellar mass required to produce 10 million solar masses of dust increases to 1 billion solar masses. 1 billion solar masses of stars, all formed, evolved, and died by 600 million years after the Big Bang. The star formation rate required is approximately 1.7 solar masses per year, sustained for 600 million years. That is higher than the Milky Way's current rate. For 600 million years without interruption, we are back to the same problem. Star formation happening too fast, too efficiently, with insufficient time for feedback to regulate the process. Theoretical astrophysicist Dasika Narayanan from the University of Florida ran simulations trying to reproduce A2744YD4's dust content. His team found that no combination of supernova yields and star formation histories can produce 10 million solar masses of dust by 600 million years without violating other observational constraints. The galaxy should not exist. But it does. Let me tell you about another anomaly, one that might be even more disturbing. The Webb galaxies are too bright, not just individually, collectively. The total luminosity of all galaxies at redshift 10 is approximately 5 times higher than predicted by standard models. Luminosity is proportional to stellar mass. More stars equals more light. If the luminosity is 5 times too high, then either the galaxies contain 5 times too many stars, or each star is 5 times brighter than expected. Option 1. More stars. This requires even higher star formation rates than we already calculated. Rates 10 or 20 times the Milky Way, sustained for hundreds of millions of years. The energy output would be so intense that the galaxies would glow in X-rays. The radiation pressure would blow gas out at velocities exceeding 1,000 kilometers per second. We should see massive outflows. Webb has detected outflows in some galaxies, but not in all. And the outflow velocities are only a few hundred kilometers per second, not enough to evacuate the gas completely. Option 2. Brighter stars. This means the stellar population is dominated by massive stars, stars above 20 solar masses. These stars are thousands of times brighter than the Sun but live only a few million years. A top-heavy initial mass function. More massive stars than low-mass stars. This is the opposite of what we observe in the modern universe, where low-mass stars outnumber massive stars by a factor of 100. Why would the initial mass function be top-heavy in the early universe? Gas metallicity. Metal-poor gas is harder to cool. When gas collapses, it heats up from compression. To fragment into small pieces, it needs to radiate away the heat. Metals like carbon and oxygen are efficient coolants. They radiate energy at specific wavelengths. Primordial gas contains no metals, only hydrogen and helium. These elements are poor coolants. Hydrogen only radiates efficiently at high temperatures, above 10,000 Kelvin. When metal-free gas collapses, it cannot cool below 10,000 Kelvin. It stays hot. Hot gas resists fragmentation. It collapses into large objects rather than small ones. This mechanism predicts that the first stars, population 3 stars, were massive, possibly 100 to 1,000 solar masses each. These stars would be incredibly bright, but they would also die quickly, within a few million years. The problem: we do not see evidence of population 3 stars in the Webb galaxies. The spectra show metal absorption lines, carbon, oxygen, nitrogen. These elements only exist if previous generations of stars have already enriched the gas. The Webb galaxies are not the first generation. They are at least the second or third generation. By that point, the gas should have enough metals to cool efficiently. The initial mass function should normalize to the standard distribution. Unless something prevented the metals from mixing. Unless the supernova ejecta did not spread uniformly. Unless pockets of metal-free gas persisted for hundreds of millions of years, continuing to form massive stars long after the first generation died. Simulations by astrophysicist John Wise from Georgia Tech showed this is possible. In a turbulent, chaotic proto-galaxy, gas flows are complex. Supernova ejecta can be confined to small regions while pristine gas continues to flow in from the cosmic web. The result is a galaxy with a heterogeneous chemical composition. Some regions rich in metals. Other regions still pristine. Star formation in the pristine regions produces massive stars. Star formation in the enriched regions produces normal stars. The total luminosity is dominated by the massive stars in pristine regions. These stars are rare but bright. They outshine the millions of low-mass stars forming in enriched regions. This model can explain the excess luminosity, but it requires a very specific set of conditions. The gas flows must be turbulent enough to prevent mixing, but organized enough to continue feeding star formation. The supernova feedback must be strong enough to enrich some regions, but weak enough to leave other regions pristine. Fine-tuning. The universe requires precise calibration to match observations. Physicists hate fine-tuning. It smells like design. Like the universe was constructed to produce specific outcomes. In science, we prefer robust mechanisms, processes that work over a wide range of parameters. But maybe the early universe was fine-tuned. Maybe the conditions after the Big Bang were calibrated to produce maximum structure formation in minimum time. Why? We do not know. Let me tell you about primordial black holes. Because they might solve everything, or make everything worse. Primordial black holes are black holes that formed in the first second after the Big Bang. Not from collapsing stars, from collapsing density fluctuations in the primordial plasma. Here's how it works. Immediately after the Big Bang, the universe was not perfectly smooth. Quantum fluctuations created regions slightly denser than average. If a fluctuation was dense enough, gravity overcame the expansion and the region collapsed. In most cases, the collapse was stopped by pressure. The region bounced, creating a sound wave. These sound waves are what we detect in the cosmic microwave background. But if the fluctuation was extremely dense, above a critical threshold, pressure could not stop the collapse. The region collapsed all the way to a black hole. These primordial black holes could have any mass, from microscopic, smaller than an atom, to supermassive, millions of solar masses. It depends on the size of the fluctuation. The key point: primordial black holes form instantly, within the first microsecond. They do not require stars. They do not require gas cooling. They just appear. If enough primordial black holes formed, they could seed galaxy formation. Gas would fall into the black holes, forming accretion disks. The accretion disks would glow with the light of stars. From a distance, this looks like a galaxy. This could explain the Webb observations. The galaxies we see are not galaxies at all. They are supermassive primordial black holes surrounded by accretion disks. The advantage: no fine-tuning required. The black holes are already there, already massive. Gas falls in and lights up immediately. No need to wait for stars to form and evolve. The disadvantage: we have no evidence that primordial black holes exist. Decades of searches have found nothing. No gravitational lensing signatures. No gravitational wave signals from primordial black hole mergers. No gamma-ray bursts from primordial black holes evaporating via Hawking radiation. The strongest constraint comes from the cosmic microwave background. If large numbers of primordial black holes formed in the early universe, they would distort the CMB. The Planck satellite measured the CMB with extraordinary precision. The distortions are absent. This limits primordial black holes to less than 1% of the dark matter density. They cannot be the dominant form of dark matter. But 1% is not zero. A small population of primordial black holes could still exist. And if they are concentrated in overdense regions, they could dominate galaxy formation in those regions, even if they are rare overall. Physicist Juan García Bellido from the Autonomous University of Madrid has championed this idea for years. In May 2023, he published a paper arguing that the Webb galaxies are consistent with clusters of primordial black holes. With masses around 100,000 solar masses, these black holes would accrete gas from the surrounding halo. The accretion luminosity would be approximately 100 times the Eddington limit. That is, 100 times brighter than a black hole should be able to shine. How is this possible? The Eddington limit is the maximum luminosity a black hole can sustain before radiation pressure blows away the infalling gas. Above this limit, accretion should shut down. But in the early universe, gas densities were much higher. The ram pressure of infalling gas could overcome radiation pressure. Super Eddington accretion becomes possible. García Bellido calculates that 10 black holes, each 100,000 solar masses, accreting at 100 times Eddington, would produce the observed luminosity of galaxies like Glass Z13. The model is testable. Primordial black holes should produce specific spectroscopic signatures, broad emission lines from gas orbiting at relativistic speeds, X-ray emission from the hot inner accretion disk, variability on timescales of hours to days as clumps of gas spiral inward. Webb's spectroscopy shows narrow emission lines. No X-ray emission has been detected, no variability has been observed. The galaxies look like galaxies, not like accreting black holes. But García Bellido argues that the observations are not yet sensitive enough. The spectroscopic resolution is limited. The X-ray telescopes cannot detect sources at redshift 14. The time coverage is insufficient to detect variability. Future observations will decide. If the galaxies show broad lines, X-rays, or variability, García Bellido is right. If they do not, primordial black holes are ruled out. Either way, we learn something. Either dark matter is made of primordial black holes, or it is not. Either option rewrites physics. There is one more possibility, one that makes physicists extremely uncomfortable, because it requires abandoning a century of successful theory. What if gravity is different in the early universe? General relativity is the most successful theory in the history of physics. Einstein published it in 1915. Since then, every prediction has been confirmed. Gravitational lensing, black holes, gravitational waves, the expansion of the universe, the bending of starlight around the sun, a perfect record for over 100 years. But general relativity assumes gravity behaves the same everywhere, in the early universe, in the late universe, near black holes, in empty space. The equations do not change. The gravitational constant is constant. What if that assumption is wrong? What if gravity was stronger in the early universe? Strong enough to pull matter together faster. Strong enough to collapse dark matter halos in half the time. Strong enough to ignite star formation 300 million years earlier than expected. This is called modified gravity, and it is heresy. To understand why, you need to understand what general relativity actually says. Einstein showed that gravity is not a force, it is geometry. Mass curves spacetime. Objects move along the curved paths. The Einstein field equations describe this precisely. They relate the curvature of spacetime to the distribution of mass and energy. 10 equations. 10 coupled nonlinear partial differential equations. They are beautiful, elegant, and they work, but they contain a parameter. The gravitational constant, represented by the letter G. This number determines the strength of gravity, how much curvature a given mass produces. We have measured G in laboratories, using torsion balances, timing how fast masses attract each other. The value is 6.67 times 10 to the power of -11. We assume this value is the same everywhere. On Earth, on Mars, in the Andromeda Galaxy, at redshift 14. But we have never actually measured G at redshift 14. We have only assumed it is the same. If G was larger in the early universe, everything changes. Dark matter halos collapse faster, gas falls in harder, star formation ignites sooner. Galaxies assemble in a fraction of the time. How much larger would G need to be? Cosmologist John Moffat from the Perimeter Institute calculated this in June 2023. To explain the Webb observations, G needs to be approximately 50% larger at redshift 10 than it is today. 50%. Not a small adjustment, a fundamental change. But there is a problem. If G changed over time, we would see evidence in other observations. The cosmic microwave background would be distorted. The abundances of light elements produced in Big Bang nucleosynthesis would be wrong. The expansion history of the universe would not match supernova data. None of these effects are observed. G appears to be constant to within 1% over the past 13.8 billion years. Unless the change is not smooth. Unless G jumped, a phase transition, a sudden change at a specific redshift. Phase transitions are common in physics. Water freezes at 0 degrees Celsius. A smooth change in temperature produces a sudden change in the material properties. The molecules rearrange. The structure transforms. Could the geometry of the universe change suddenly at redshift 12? String theory allows for this. In string theory, space-time has extra dimensions. Dimensions we do not see because they are curled up, compactified. The size of the extra dimensions determines the strength of gravity in the visible dimensions. If the extra dimensions change size, gravity changes strength. This is called moduli stabilization. The moduli are fields that describe the size and shape of the extra dimensions. If these fields are not perfectly stable, they can roll, evolve, change over time. A moduli phase transition could cause G to jump. But string theory predicts these transitions happen much earlier, in the first microsecond after the Big Bang. Not at redshift 12, not 300 million years later, unless the moduli are rolling slowly, barely moving. Then a small perturbation, a random fluctuation, could trigger a sudden transition at any time. This is speculation piled on speculation. String theory is not proven. Moduli fields are hypothetical. Phase transitions at redshift 12 are invented to fit the data. Occam's razor is screaming. But there is another approach. One that does not modify general relativity. One that modifies the thing general relativity acts upon. What if dark matter is not matter at all? In 1983, physicist Mordechai Milgram proposed modified Newtonian dynamics, MOND. The idea is simple. At low accelerations, gravity behaves differently than Newton predicted. Newton's second law says, force equals mass times acceleration. F equals m times a. This works perfectly on Earth, on the Moon, in the solar system, everywhere we have tested it directly. But galaxy rotation curves are not tested directly. They measure stars moving at accelerations far lower than anything we experience on Earth. Accelerations of approximately 10 to the power of -10 meters per second squared. That is 1/10,000,000th of Earth's surface gravity. At accelerations this low, Milgram argues, Newton's law breaks down. Gravity becomes stronger than expected. The modified equation is F equals m times a when a is large. But when a drops below a critical value, called a0, the equation becomes F equals m times a0 times the square root of a divided by a0. The critical acceleration a0 is approximately 1.2 times 10 to the power of -10 meters per second squared. This single number, chosen to fit galaxy rotation curves, explains observations across thousands of galaxies without requiring dark matter. MOND works disturbingly well. For individual galaxies, MOND predicts rotation curves perfectly, better than dark matter models. Dwarf galaxies, spiral galaxies, elliptical galaxies. MOND gets them all right. But MOND fails for galaxy clusters. The modified gravity is not strong enough to hold clusters together. You still need additional mass, either dark matter or something else. MOND also fails to explain the cosmic microwave background. The acoustic peaks depend on the ratio of dark matter to normal matter. MOND does not predict these peaks correctly. For 40 years, MOND has been a curiosity, a phenomenological fit, not a fundamental theory. No one knows why gravity would change behavior at a specific acceleration. It is just an observation. But the Webb galaxies might revive MOND, because MOND makes a prediction that dark matter does not. In MOND, structure forms faster. Galaxies assemble earlier. The effective gravitational force is stronger at low accelerations. This pulls matter together more efficiently. Physicist Stacy McGaugh from Case Western Reserve University published a paper in July 2023 showing that MOND predicts bright galaxies at redshift 14 naturally. No fine-tuning, no modified dark matter, just the standard MOND equations applied to the early universe. The galaxies that shock astronomers are exactly what MOND expects. But McGaugh's paper has been largely ignored, because MOND does not fit into the larger cosmological framework. It cannot explain gravitational lensing without additional assumptions. It cannot explain the cosmic microwave background without dark matter. MOND is incomplete. It is not a theory, it is a correction factor. A patch on Newton's laws. And patches do not win Nobel Prizes. Unless MOND is a clue, A hint that gravity really does behave differently at low accelerations. Not because Newton was wrong, but because dark matter itself generates the modified behavior. This is called emergent gravity. The idea that gravity is not fundamental but emerges from deeper physics. Theoretical physicist Erik Verlinde from the University of Amsterdam has developed this idea for a decade. He argues that gravity is an entropic force, a statistical effect arising from the quantum entanglement of space-time. In Verlinde's model, dark matter does not exist as particles. It exists as additional entropy in space-time, extra information encoded on cosmic horizons. This entropy creates an effective gravitational force that mimics dark matter. At low accelerations, the entropic contribution dominates. This reproduces MON. At high accelerations, the entropic contribution becomes negligible. This reproduces general relativity. Verlinde published detailed predictions in 2016. His theory predicts galaxy rotation curves, predicts gravitational lensing, predicts the cosmic microwave background, all without dark matter particles. The theory was tested in 2017 by analyzing 500 galaxies. The results were mixed. Some galaxies fit Verlinde's predictions. Others did not. The theory was declared inconclusive. But the Webb observations might change that. If Verlinde's entropy explanation allows faster structure formation, it could explain the impossible galaxies. The additional entropy would seed galaxy formation earlier, allowing structure to assemble in half the time. Verlinde has not yet published a paper on this. The community is waiting. The problem with all modified gravity theories is that they are playing catch-up. They are invented to explain observations that standard theories cannot. That is not how science is supposed to work. Science progresses through prediction. Einstein predicted gravitational waves in 1916. They were detected in 2015, 99 years later. That is a successful theory, a theory that predicts observations before they happen. Modified gravity theories predict nothing new. They only explain existing anomalies. This makes them unfalsifiable. Every time a new anomaly appears, modified gravity theorists adjust their equations to fit. The theory evolves to match the data. This is called fine-tuning, and it is a sign of a dying theory, or a theory that was never alive. Dark matter has the opposite problem. It was invented to explain galaxy rotation curves. Then it successfully predicted gravitational lensing, predicted the cosmic microwave background, predicted large-scale structure. It has passed every test except one. We have never detected a dark matter particle. Dozens of experiments are searching. The Large Hadron Collider, deep underground detectors like Xenon and LOX, space-based detectors like AMS-02, all looking for WIMP particles. 40 years of searching, billions of dollars, thousands of scientists, zero detections. The parameter space is shrinking. Each failed experiment rules out a range of WIMP masses and interaction cross-sections. The allowed region is getting smaller, tighter, more constrained. Some physicists are starting to worry. What if WIMPs do not exist? What if dark matter is something else? Axions, sterile neutrinos, primordial black holes, something we have not thought of yet. Or what if dark matter does not exist at all? What if gravity really is modified? The Webb observations force this question into the open. Because standard dark matter models do not predict these galaxies, they should not exist. And yet they do. Either dark matter behaves differently than we calculated, or dark matter does not exist, or our observations are wrong. The third option deserves consideration. What if the galaxies are not at redshift 14? What if the distance measurements are incorrect? Redshift is measured spectroscopically. You identify emission lines from hydrogen or oxygen. You measure their observed wavelength. You compare it to the rest wavelength measured in laboratories on Earth. The difference is the redshift. Redshift equals observed wavelength minus rest wavelength divided by rest wavelength. This number tells you how much the universe expanded while the light was traveling. For Jade's GSZ14, the Lyman alpha line is observed at 2.16 microns. The rest wavelength is 0.1216 microns. The redshift is 14.32. This measurement has been confirmed independently by multiple teams using different instruments. The error bars are small, plus or minus 0.1. The galaxies are really that far away. But distance is not the only factor. Brightness matters too. A galaxy can appear bright for two reasons. It is intrinsically luminous, or it is gravitationally lensed. Gravitational lensing occurs when a massive object, like a galaxy cluster, bends light from a background source. The bending focuses the light, magnifying the background galaxy, making it appear brighter and larger than it actually is. The Hubble Deep Field famously showed hundreds of lensed galaxies, arcs, and multiple images distorted by foreground clusters. Some galaxies were magnified by factors of 10 or more. Could the Webb galaxies be lensed? Could their brightness be artificially inflated? Astronomer Hao-Jing Yan from the University of Missouri analyzed the morphologies of 20 Webb galaxies at redshift greater than 10. He looked for signs of lensing, distortion, elongation, multiple images. He found none. The galaxies are compact, circular, isolated, no evidence of lensing. This does not completely rule out lensing. Weak lensing can magnify galaxies by factors of 2 or 3 without obvious distortion. But weak lensing cannot explain factors of 10 or 20, cannot explain 80 times too many galaxies. The galaxies are genuinely bright, genuinely massive, genuinely impossible. So we return to dark matter, because dark matter is still the leading explanation. The simplest explanation, the explanation that requires the fewest new assumptions. But the dark matter required to explain Webb is not the dark matter we have been searching for. It is faster, denser, more interactive, different. Cosmologist Wayne Hugh from the University of Chicago summarized the situation in an August 2023 review paper. He listed 6 possible solutions to the impossible early galaxy problem. 1. Dark matter clumps faster due to enhanced initial density fluctuations. 2. Dark matter is self-interacting, accelerating collapse. 3. Dark matter is warm, allowing large-scale collapse while suppressing small-scale structure. 4. Dark matter decays, releasing energy that triggers early star formation. 5. Primordial black holes seed galaxy formation. 6. Gravity is modified at low accelerations or high redshifts. Each solution has problems. Each requires abandoning or modifying a fundamental assumption. None is clearly better than the others. Hugh concludes that we need more data, more Webb observations, deeper surveys, higher spectroscopic resolution, measurements of gas kinematics, detection of molecular lines. And we need new experiments. Dark matter detectors searching for different particles, gravitational wave detectors looking for primordial black hole mergers, cosmic microwave background experiments measuring smaller angular scales. The answer will come, eventually. But until then, we are suspended in uncertainty. The universe showed us something we did not predict, something our best theories cannot explain. This has happened before in the history of science. In the late 1800s, astronomers measured the orbit of Mercury. The planet did not move as Newton's laws predicted. The perihelion precessed shifted 43 arcseconds per century, more than calculations allowed. For decades, astronomers invented explanations. An unseen planet, Vulcan, orbiting inside Mercury, pulling on Mercury gravitationally, explaining the precession. They searched for Vulcan, pointed telescopes at the sun during solar eclipses, looking for a tiny world silhouetted against the solar disk. They never found it. Vulcan did not exist. Then, in 1915, Einstein published General Relativity. The theory predicted Mercury's precession exactly. No Vulcan required. Just a better understanding of gravity. The lesson: when observations conflict with theory, the theory is usually wrong, not the observations. We are in that moment again. The observations say galaxies exist at redshift 14. The theory says they should not. History suggests the theory is wrong. But which part of the theory? Dark matter? Gravity? Structure formation? Star formation? All of it? The answer will redefine cosmology. We'll rewrite textbooks. We'll invalidate thousands of papers. And it will happen soon. Because Webb is not finished. The telescope has a mission lifetime of 10 years. Maybe 20 if the fuel lasts. It will survey deeper, observe more galaxies, measure more spectra. Every observation constrains the theories, eliminates possibilities, narrows the solution space. Within 5 years, we will know. Either dark matter is self-interacting, or dark matter is warm, or dark matter is decaying, or primordial black holes exist, or gravity is modified. One of these is true. The universe is forcing us to choose. Let me tell you what will happen if each is correct. If dark matter is self-interacting, particle physicists will need to invent a new particle, a new force. The standard model will expand. New experiments will be designed. Detectors buried deeper underground, accelerators built larger. The search will continue for another 50 years. If dark matter is warm, the mass of the particle is constrained to a narrow range, between 1 and 10 kilo-electron volts. This is testable. Sterile neutrino searches will intensify. X-ray telescopes will look for decay lines. Cosmological simulations will be rerun with warm dark matter. The small-scale structure crisis will be solved. But new questions will emerge. If dark matter decays, the implications are profound. The universe today is not the universe of the past. Dark matter evolved, changed. The density decreased. The properties shifted. Every cosmological simulation must be redone. Every distance measurement recalibrated. The expansion history recalculated. And the decay products, where are they? What particles are dark matter decaying into? Can we detect them? If primordial black holes exist, the Big Bang was not smooth, not uniform. Massive density fluctuations existed at the quantum level. Fluctuations large enough to collapse into black holes. This requires inflation, the rapid expansion in the first microsecond, to have been violent, chaotic, producing huge variations in density. This is testable. Gravitational wave detectors like LIGO can detect primordial black hole mergers. They would have specific mass ratios, specific merger rates, specific gravitational wave signatures. If primordial black holes make up even 1% of dark matter, LIGO will eventually detect them. If gravity is modified, general relativity is incomplete. Not wrong. Incomplete. It works at high accelerations but fails at low accelerations. This is similar to Newtonian gravity, which works at low speeds but fails at high speeds near the speed of light. Einstein corrected Newton. Now something must correct Einstein. The correction could come from quantum gravity, from string theory, from loop quantum gravity, or from something completely new. Whatever it is, it will unify gravity with quantum mechanics, solve the cosmological constant problem, explain dark energy. It will be the greatest discovery in theoretical physics since general relativity itself. All of these outcomes are revolutionary. All of them rewrite physics. There is no conservative solution, no way to explain Webb without abandoning something fundamental. This is what makes science terrifying and beautiful. Reality does not care about our theories, does not care about our careers or our cherished beliefs. Reality simply is. And when reality contradicts theory, reality wins. The galaxies are not just impossible, they are disturbing in specific ways that reveal deeper problems. Galaxy designation: Rebels 25, redshift 7.5, age 680 million years after the Big Bang. This galaxy was discovered by the ALMA telescope in Chile before Webb launched. When Webb observed it, the results were bizarre. Rebels 25 is a starburst galaxy. It is forming stars at approximately 300 solar masses per year. That is 200 times faster than the Milky Way. The entire galaxy will consume its gas reservoir in approximately 10 million years at this rate. But here's the disturbing part. The gas reservoir is enormous, approximately 10 billion solar masses of molecular hydrogen, enough fuel to sustain star formation at current rates for 30 million years. Where did this gas come from? In the Standard Model, gas is accreted from the cosmic web. It flows along dark matter filaments into the galaxy's halo. But the accretion rate depends on the size of the halo and the density of the surrounding filament. For a galaxy at redshift 7.5, the maximum accretion rate is approximately 10 solar masses per year. Rebels 25 is consuming gas at 300 solar masses per year. The consumption rate is 30 times higher than the supply rate. The galaxy is eating itself faster than the universe can feed it. Astrophysicist Jacqueline Hodge from Leiden University led the analysis. She calculated that Rebels 25 must have assembled its gas reservoir earlier. Much earlier, before redshift 10, when the universe was only 500 million years old. But gas at that epoch is hot, 10,000 Kelvin. Hot gas cannot form molecules. Molecular hydrogen requires cold temperatures below a few hundred Kelvin to form efficiently. How do you cool 10 billion solar masses of gas in less than 200 million years? Cooling requires radiation. The gas must radiate energy into space. For atomic hydrogen, the primary cooling mechanism is the Lyman alpha line, a photon emitted when an electron drops from the second energy level to the ground state. But Lyman alpha cooling is slow. The cooling time for diffuse gas at 10,000 Kelvin is approximately 1 billion years. There has not been enough time. Unless the gas is not diffuse. Unless it is compressed. Dense gas cools faster because collisions between atoms are more frequent. More collisions means more excitations. More excitations means more photons. More photons means faster cooling. What could compress the gas? Shock waves, supernova explosions, stellar winds, active galactic nuclei. All of these processes inject energy into the gas, creating shock waves that propagate outward at thousands of kilometers per second. But these processes also heat the gas. Compression heats. Shocks heat. How do you compress gas without heating it? The answer is not clear. The physics does not work. The galaxy should not have this much cold molecular gas this early, unless the gas never heated up in the first place. Unless it fell into the galaxy cold, directly from the cosmic web. Without shocking, without heating. Cold mode accretion taken to the extreme. Simulations show this is possible if the dark matter halo has a specific structure, if the halo has low-density channels extending outward along filaments. Gas flowing through these channels remains cold, stays molecular, arrives at the galaxy ready to form stars immediately. But these low-density channels are fragile. Turbulence destroys them, mergers disrupt them. They exist only in halos that have not experienced recent violent events. Rebels 25 shows signs of recent merger activity. The morphology is disturbed, asymmetric. The gas distribution is chaotic. This should have destroyed any cold mode channels. Yet the galaxy has 10 billion solar masses of cold molecular gas. Impossible gas. Another disturbing example. Galaxy designation SPTSJ0349-5301. Redshift 5.7. Age 1 billion years after the Big Bang. This galaxy is not as distant as the Webb record holders, but it is more massive. The stellar mass is approximately 350 billion solar masses. That is more than twice the Milky Way's current stellar mass. At 1 billion years, to build 350 billion solar masses of stars in 1 billion years requires a star formation rate of 350 solar masses per year sustained continuously from the moment the universe began. But star formation is not continuous. It is episodic, bursty, driven by mergers, triggered by instabilities. Real star formation histories show peaks and valleys. To produce 350 billion solar masses with realistic episodic star formation requires peak rates of 1,000 solar masses per year, maintained for hundreds of millions of years during active periods. 1,000 solar masses per year. That is 1,000 new stars every single year. 3 stars per day. 1 star every 8 hours. The energy output would be apocalyptic. The galaxy would shine with the light of 1 trillion suns. The radiation pressure would be so intense that gas could not collapse, could not cool, could not form additional stars. This is called the Eddington limit for starburst galaxies. Above a certain luminosity, radiation pressure blows gas out of the galaxy faster than gravity can pull it in. Star formation self-regulates, self-limits. SPTSJ0349-5301 exceeds the Eddington limit by a factor of 10. How? Theoretical astrophysicist Philip Hopkins from Caltech proposed a mechanism called momentum-driven winds. The idea is that radiation does not blow gas directly. Instead, it accelerates dust grains. The dust grains collide with gas atoms, transferring momentum. The gas accelerates, flows outward, escapes the galaxy. But dust is fragile. Radiation destroys it. Ultraviolet photons break molecular bonds. Dust grains vaporize, turn back into atoms. Once the dust is gone, radiation cannot couple to the gas efficiently. The wind shuts down. Maintaining momentum-driven winds requires continuous dust production. Supernovae must constantly create new dust to replace the dust destroyed by radiation. At 1,000 solar masses per year star formation, approximately 10 supernovae explode per year. Each produces approximately 1 solar mass of dust. That is 10 solar masses of dust per year, but the radiation field is also destroying approximately 100 solar masses of dust per year. The destruction rate is 10 times higher than the production rate. The galaxy should run out of dust within a few million years. Then radiation pressure would blow away the gas. Star formation would stop. SPTSJ SJ0349-5301 has sustained this rate for hundreds of millions of years. The dust did not run out. The star formation did not stop. Something is shielding the dust, protecting it from radiation, allowing it to survive long enough to drive winds. What could shield dust? More dust. If dust is dense enough, the outer layers absorb radiation, protecting the inner layers. Dust shields itself. But this requires enormous dust columns, optical depths exceeding 100. That means light must pass through 100 dust grain lengths before escaping the galaxy. In practice, this makes the galaxy invisible. All optical and ultraviolet light is absorbed. The galaxy appears dark, a shadow, a void. Except we see it. We detect it because dust re-emits absorbed energy as infrared. The galaxy glows in the infrared. This is how SPT SJ0349-5301 was discovered by the South Pole Telescope observing sub-millimeter wavelengths. The galaxy is so dust-rich that it is invisible in optical light. Webb cannot see it directly, only its infrared glow. This raises a terrifying question. How many galaxies are we missing? If SPT-SJ0349-5301 is representative, then many massive early galaxies are hidden by dust, invisible to optical telescopes, undetectable even to Webb unless you observe in the far infrared. The surveys we have conducted miss these galaxies. They are biased toward clean, dust-free systems, toward galaxies we can see. The true number of massive early galaxies could be 10 times higher than we measure, 100 times higher. We do not know. Astronomer Caitlin Casey from the University of Texas leads the Cosmos Webb survey. Her team is using Webb's infrared capabilities to search for dust-obscured galaxies at high redshift. Preliminary results suggest the population is enormous. For every optically bright galaxy at redshift 10, there may be 3 to 5 dust-obscured galaxies. Invisible galaxies. Hiding in plain sight. If this is confirmed, the impossible early galaxy problem becomes 3 to 5 times worse. Not 10 galaxies at redshift 10, 50 galaxies. Not 80 times too many. 400 times too many. The universe did not just wake up early, it exploded into existence. Let me tell you about a galaxy that should not exist for a completely different reason. Galaxy designation GNZ11. Redshift 11.1. Age 420 million years after the Big Bang. This galaxy has been known since 2016. Discovered by Hubble. Confirmed by Webb. GNZ11 is not the most distant galaxy, not the most massive, but it has a property that makes it unique. The spectrum shows a black hole, a supermassive black hole, mass, approximately 2 million solar masses at 420 million years. Supermassive black holes take time to grow. They start as stellar mass black holes, 10 to 100 solar masses. They accrete gas from their surroundings, double their mass every few million years if they accrete at the maximum rate. Starting from 100 solar masses and doubling every 5 million years, it takes approximately 65 million years to reach 1 million solar masses. Another 5 million to reach 2 million. 70 million years. That is the absolute minimum growth time assuming continuous accretion at the Eddington limit, with perfect efficiency and no interruptions. GNZ11's black hole exists at 420 million years. Subtract 70 million years. The seed black hole must have formed at 350 million years. But where did the seed come from? Stellar mass black holes form from collapsing stars, massive stars, above 20 solar masses. These stars take approximately 3 million years to evolve from birth to supernova, so you need stars to form at 347 million years. To live 3 million years, to explode, to leave behind a black hole, 347 million years after the Big Bang. The universe is still in the epoch of reionization. The first galaxies are just turning on. And in the middle of this chaos, a star forms, lives, dies, creates a black hole, and that black hole grows to 2 million solar masses in 70 million years. This timeline is possible. Barely. If everything happens perfectly. But here is the problem. You need one black hole to reach 2 million solar masses. But you also need the galaxy. GNZ11 contains approximately 1 billion solar masses of stars. Those stars also need to form, also need time to accumulate. The galaxy and the black hole are growing simultaneously, competing for the same gas. The black hole accretes gas. The galaxy forms stars from gas. They are both consuming the fuel supply. In the modern universe, black holes and galaxies grow together. There is a relationship. The black hole mass is approximately 0.2% of the galaxy's stellar mass. For GNZ11, this ratio predicts a black hole mass of 2 million solar masses, which is exactly what we observe. The ratio holds at 420 million years after the Big Bang. The relationship between black holes and galaxies is already established. Already calibrated. This implies the relationship is fundamental, not an accident, not a coincidence, a law. But we do not understand why. Why is the black hole mass always 0.2% of the stellar mass? Why not 1%? Why not 0.1%? The standard explanation is feedback. The black hole accretes gas, heats it, launches jets. The jets blast through the galaxy, blow gas away, stop star formation, regulate the growth. But feedback takes time to propagate. The jets travel at relativistic speeds, 90% the speed of light. But even at this speed, crossing a galaxy takes thousands of years. During those thousands of years, the black hole continues accreting. The galaxy continues forming stars. Both systems grow unchecked until the feedback catches up. This creates a delay, a lag between black hole growth and stellar growth. The two systems should be out of sync, oscillating. First, the black hole grows. Then, feedback stops it. Then the galaxy grows. Then more gas falls in. Then the black hole grows again. We should see galaxies with too much stellar mass and small black holes. Galaxies with huge black holes and insufficient stars. The ratio should vary wildly from galaxy to galaxy. It does not. The ratio is constant, locked at 0.2% across billions of years of cosmic time. From redshift 11 to redshift 0. Why? No one knows. This is called the M-sigma relation. The black hole mass correlates with the velocity dispersion of stars in the galaxy's bulge. Tighter correlation than any other relationship in astrophysics. It is as if the black hole and the galaxy know about each other. As if they are communicating, coordinating their growth, maintaining the ratio deliberately. But black holes and galaxies do not communicate. Information cannot travel faster than light. By the time a star on the edge of the galaxy receives information about the black hole's growth, the black hole has already changed. Unless the coordination happens through dark matter, the black hole sits in a dark matter halo. The galaxy also sits in the same halo. Both grow by accreting material from the halo. If the halo's structure determines the accretion rate for both systems, then both will grow in lockstep automatically. This is the leading explanation. The dark matter halo is the mediator, the invisible hand coordinating visible matter. But if dark matter is modified, if dark matter is self-interacting or warm or decaying, then the halo structure changes. The mediation breaks down. The M-sigma relation should not hold in the early universe. GNZ11 says it does hold. At redshift 11, at 420 million years. The relationship is already in place, already locked in. This is evidence that dark matter has not changed, has not evolved. Behaves the same at redshift 11 as at redshift 0, which means self-interacting dark matter is less likely. Decaying dark matter is less likely. The properties must be stable across 13 billion years, unless GNZ11 is not typical, unless it is an outlier. A rare exception that happens to follow the modern M-sigma relation by coincidence. To know if it is typical, we need more examples. More black hole masses at high redshift, more measurements, more data. Webb is collecting this data now. By the end of 2024, we will have measurements of 50 black holes at redshift greater than 6. By 2025, 100 measurements. By 2026, 200. The M-sigma relation will either hold or break. If it holds, dark matter is stable. If it breaks, dark matter evolves. Either outcome is revolutionary. Astronomer Roberto Maialino from Cambridge University is leading this effort. His team uses Webb's spectroscopy to measure black hole masses from the width of emission lines, hydrogen lines, oxygen lines, magnesium lines. The width tells you the velocity of gas orbiting the black hole. The velocity tells you the mass. It is straightforward, precise, reliable. Maialino has measured 15 black holes so far, all at redshift greater than 7. All follow the M-sigma relation. All have black hole masses around 0.2% of the stellar mass. 0 out of 15 deviate. The relationship holds perfectly so far. But 15 is a small sample, statistically insignificant. We need hundreds to confirm the trend, or to find the outliers. The galaxies, where the relationship breaks, those outliers, if they exist, will tell us when and how the relationship formed. Will point to the mechanism. Will reveal what dark matter is doing. Let me tell you what makes this all psychologically disturbing beyond just the scientific implications. For 100 years, cosmology has been a story of continuous surprise. Every decade, we discover something that forces us to rewrite the textbooks. 1920s. The universe is expanding, not static, growing. 1930s. Galaxies contain invisible mass. Dark matter exists. 1960s. The cosmic microwave background is detected. The Big Bang is confirmed. 1998. The expansion is accelerating. Dark energy exists. 2022. Galaxies exist at impossible times. Everything is wrong. Each discovery makes the universe stranger, more alien, less intuitive. We are not discovering a universe that matches human intuition. We are discovering a universe that violates it systematically. This is not a coincidence. Human intuition evolved to handle objects moving at meters per second over distances of kilometers. Our brains are optimized for hunting, for throwing spears, for tracking prey. We are not evolved to understand the universe at cosmic scales, not evolved to grasp 13 billion years, not evolved to imagine 10 to the power of 23 stars. And yet we are forced to. The universe does not care about our cognitive limitations. It simply is what it is. This creates a psychological tension. The universe we study is not the universe we can visualize. We deal with it mathematically, abstractly, through equations and simulations. But equations do not feel real. Simulations do not feel visceral. We lose connection to the subject. The universe becomes a game, a puzzle, a set of numbers to manipulate. And then Webb returns an image, a photograph, and suddenly the abstraction becomes real. You see a galaxy, red and distant, but there, real. A physical object containing hundreds of billions of stars. Each star potentially orbited by planets. Each planet potentially inhabited by something looking up at their own night sky wondering if they are alone. The abstraction collapses into reality. The numbers become worlds. And you realize the universe is not a puzzle. It is a place. An infinite place containing an infinite number of places. And you are in one of them, right now, reading these words. While that galaxy 13 billion light-years away is still there, still spinning, still forming stars, even though you will never see it, except as a smudge of red light. This realization is disturbing because it makes you small, not metaphorically small, literally small. You are one organism on one planet orbiting one star in one galaxy among 2 trillion galaxies. Your entire life spans less than 100 years. The universe has existed for 13.8 billion years. You occupy 0.00007% of cosmic time. From the universe's perspective, you do not exist. You are a quantum fluctuation, a brief spike in entropy, a temporary configuration of atoms that will dissipate when you die. And yet you are the one observing the universe. The universe is not observing itself. You are. Your consciousness, temporary as it is the phenomenon that allows the universe to know itself. This is the paradox at the heart of cosmology. The universe is vast and indifferent. But understanding requires consciousness, and consciousness requires smallness, requires mortality. Requires being a brief, flickering pattern of matter that can look at the stars and ask why. The impossible galaxies make this paradox sharper, because they reveal that we do not understand even the basic story of how structure formed, how matter clumped, how galaxies assembled. We thought we knew. We had a timeline, a narrative. First stars at 150 million years, first galaxies at 500 million years, mature galaxies at 1 billion years. Neat, clean, logical. Wrong. The narrative we built was a scaffolding, a temporary structure to make sense of observations we did not fully understand. And now the observations have outgrown the scaffolding. The structure is collapsing. This is not the first time this has happened. Newtonian mechanics was a scaffolding. It worked for 200 years, predicted planetary orbits, explained tides, allowed engineers to build bridges and calculate trajectories. Then Mercury's orbit did not fit. The perihelion precessed 43 arcseconds per century too much. The scaffolding cracked. Einstein built a new scaffolding. General relativity, curved spacetime, gravity as geometry. It explained Mercury, predicted gravitational waves, predicted black holes, worked perfectly for 100 years. Now the Webb galaxies do not fit. The scaffolding is cracking again. What comes next? What replaces general relativity and cold, dark matter? We do not know yet. But we know it will be stranger than what came before, because that is the pattern. Each revolution makes the universe less intuitive, more abstract, further from common sense. Newton's universe made sense. Objects fall because they are attracted. The math was simple. F equals g times m1 times m2 divided by r squared. Anyone can understand this. Einstein's universe makes less sense. Objects fall because space-time is curved. What does that mean? How do you visualize curved space-time? You cannot. You can draw analogies, rubber sheets, bowling balls, but these are metaphors. The reality is mathematical. The Einstein field equations, 10 coupled nonlinear partial differential equations, most people cannot even read them. The next universe will make even less sense. It will require mathematics that does not exist yet, concepts that have no analogies, no metaphors, no way to visualize them. And yet it will be true. It will match observations. It will predict new phenomena. It will work. Science does not care about human understanding. It cares about predictive power, about matching measurements, about being less wrong than the previous theory. We are entering a phase where the universe becomes incomprehensible to non-specialists, where understanding requires a PhD in theoretical physics, where the gap between expert knowledge and public knowledge becomes unbridgeable. This is dangerous, because democracies require informed citizens, require people who can evaluate evidence, can distinguish truth from fiction, can understand why scientists believe what they believe. But how do you explain modified dark matter to someone who does not know calculus? How do you explain self-interacting cross-sections? How do you explain the difference between cold and warm dark matter when both are invisible? You cannot. Not really. You can give analogies, metaphors, simplified explanations. But these are lies, useful lies, lies that point toward truth, but still lies. The real explanation is mathematical, and mathematics is a language most people do not speak. This creates a crisis of authority. Scientists say dark matter exists. The public asks for proof. Scientists point to galaxy rotation curves, mathematical derivations, gravitational lensing observations. The public does not understand, cannot evaluate the evidence, must trust the experts. But trust is fragile, especially when the experts keep changing their story. First, dark matter is cold. Then, maybe it is warm. Then maybe it is self-interacting. Then maybe it does not exist at all. From the outside, this looks like confusion. Like scientists do not know what they are talking about. Like the whole field is built on guesses. From the inside, this is how science works. Hypothesis, test, revise, repeat. The story changes because our understanding improves, because new data arrives, because we are getting less wrong over time. But the public does not see this. They see scientists contradicting themselves, changing positions, admitting uncertainty. And uncertainty is uncomfortable. Humans crave certainty, crave simple answers, crave narratives that do not change. Religion provides this. God created the universe. That is the answer. It does not change, does not require updates, does not depend on new telescopes or revised calculations. Science cannot compete with this. Science offers provisional truths, best current explanations subject to revision, knowledge that will be obsolete in 50 years. This is why conspiracy theories thrive, why flat Earth movements persist, why people reject evolution and climate science and vaccines. Not because the evidence is weak, the evidence is overwhelming, but because the evidence is complex, requires trust in experts, requires accepting that the universe is stranger than intuition suggests. The Webb galaxies make this worse, because now even the experts are confused. Even the PhD astrophysicists are scrambling for explanations. Even the theorists who built the models are admitting the models are wrong. If the experts do not know, why should anyone trust them? This is the danger. This is how science loses authority, loses credibility, becomes just another opinion, another belief system competing in the marketplace of ideas. The solution is not to hide uncertainty, not to pretend we know more than we do. The solution is to explain why uncertainty is okay, why revising theories is a feature, not a bug, why admitting you are wrong is the most scientific thing you can do. But this requires trust, requires the public to understand that science is a process, not a collection of facts, a method for approaching truth asymptotically, getting closer and closer without ever arriving completely. The Webb observations are a test, not just of our cosmological models, but of our ability to communicate science, to explain why impossibility is exciting, why anomalies are opportunities, why being wrong is the only way to eventually be right. Let me tell you what happens next. What observations will decide between the competing theories? Webb is currently conducting the JADE survey, the JWST Advanced Deep Extragalactic Survey, a multi-year program observing two deep fields continuously, building up thousands of hours of exposure time. By the end of 2025, JADES will have cataloged over 5,000 galaxies at redshift greater than 6, hundreds at redshift greater than 10, dozens at redshift greater than 12. This sample size will reveal whether the bright galaxies are common or rare, whether the number density we measured in the first surveys is typical or a fluke. If bright galaxies are common, dark matter must be modified, must clump faster, must behave differently than standard models predict. If bright galaxies are rare, we got lucky. Pointed Webb at an overdense region. The standard models survive. No revolution required. The JADES team will also measure stellar masses more precisely, using multi-wavelength photometry, fitting stellar population models, determining ages and star formation histories. If the stellar masses are lower than initially estimated, the problem is less severe. The galaxies are bright because they contain massive hot stars, not because they contain too many total stars. If the stellar masses are higher, the problem is worse. The galaxies are genuinely too massive for the standard timeline. Spectroscopy will determine gas metallicities, oxygen to hydrogen ratios, carbon to oxygen ratios. These ratios reveal how many generations of stars have lived and died. If metallicities are high, multiple generations have already occurred. The galaxies are old. Started forming early, this supports fast structure formation models. If metallicities are low, the galaxies are first generation. The stars are massive and short-lived. This supports top-heavy initial mass function models. Kinematics will measure rotation velocities, how fast stars are orbiting the galactic center. This reveals the dark matter halo mass, compares dynamical mass to stellar mass. If dynamical masses are much larger than stellar masses, the galaxies live in massive dark matter halos. This is consistent with standard cold dark matter. If dynamical masses are similar to stellar masses, dark matter is not dominant. Either the halos are less massive than predicted, or dark matter does not exist. All of these measurements are currently underway. Results are arriving monthly. Papers are being published weekly. The field is moving fast. By the end of 2026, we will have answers, not complete answers, not final answers, but constraints, limits, boundaries that rule out some theories and support others. The European Space Agency is also planning a mission. The Euclid Space Telescope, launched July 2023, currently mapping the large-scale structure of the universe. Euclid will observe billions of galaxies, measure their positions, their redshifts, their shapes. Build a three-dimensional map of the cosmic web. This map will reveal whether dark matter is clumped the way standard models predict, whether voids are as empty as expected, whether filaments are as prominent as simulations show. If the structure matches predictions, cold dark matter is correct. The models are right. The impossible galaxies are a localized anomaly. If the structure does not match, the models are wrong. Dark matter is modified. The impossible galaxies are the tip of an iceberg. Ground-based telescopes are also contributing. The Atacama Large Millimeter Array in Chile. ALMA, observing molecular gas in distant galaxies. ALMA can detect carbon monoxide lines, CO. These lines reveal the mass of molecular hydrogen, the fuel available for star formation. If distant galaxies have large gas reservoirs, they can sustain high star formation rates. The impossible galaxies become plausible. If gas reservoirs are small, the star formation rates are unsustainable. The galaxies must be accreting gas faster than models predict. Or the gas is coming from sources we have not identified. The Vera C. Rubin Observatory in Chile will begin operations in 2025. The Legacy Survey of Space and Time, LSST. This telescope will photograph the entire visible sky every 3 nights for 10 years. LSST will detect transient events, supernovae, tidal disruption events, gamma ray bursts, any object that brightens or fades over time. If the early universe is filled with massive stars, LSST will detect their deaths. Supernova rates at high redshift will be measurably higher than predicted. If supernova rates are normal, the stellar populations are not dominated by massive stars. The initial mass function is not top-heavy. The Square Kilometre Array, SKA, currently under construction in Australia and South Africa, will observe neutral hydrogen at radio wavelengths. SKA will map the distribution of hydrogen gas before reionization during the Dark Ages. Will reveal how gas was flowing into early galaxies, how dark matter halos were accreting material. If gas flows were stronger than predicted, galaxies could assemble faster, could form stars earlier, could explain the impossible galaxies. If gas flows were normal, something else accelerated structure formation, something internal to the galaxies, or something about dark matter itself. All of these telescopes, all of these observations, all pointing at the same question: why did galaxies form so early? The answer will come from data, from measurements, from photons that traveled 13 billion years to reach our detectors, from light that left those galaxies when the universe was young and has been racing through expanding space ever since. Those photons carry information, encoded in their wavelengths, their brightnesses, their arrival times, information about the conditions in the early universe, about the properties of dark matter, about the nature of gravity. We are decoding that information now, translating photons into knowledge, building a picture of the early universe one observation at a time. And that picture is not what we expected, not what our theories predicted, not what decades of cosmological simulations prepared us for. The universe was more violent than we thought, more active, more eager to build structure, more impatient to form galaxies. Why? That is the question. That is what keeps cosmologists awake at night. That is what drives theorists to invent new particles and new forces and new modifications to gravity. Because there must be a reason. The universe does not violate its own laws, does not act randomly, does not form galaxies early just to surprise astronomers. There is a mechanism, a process, a chain of cause and effect that produce these galaxies. We simply have not discovered it yet, but we will, because that is what science does. It finds mechanisms, explains processes, reveals the hidden machinery of nature. The machinery that built galaxies 13 billion years ago is the same machinery operating today, the same dark matter, the same gravity, the same thermodynamics. The laws have not changed. Only our understanding has changed, and it is changing fast. Within your lifetime, this mystery will be solved. The impossible galaxies will become possible. The mechanism will be revealed. Textbooks will be rewritten. And then new telescopes will discover new impossibilities. New galaxies that should not exist. New phenomena that violate the updated theories. Because that is how science progresses. Not toward final truth, toward deeper mystery. Each answer revealing new questions. Each solved problem exposing harder problems. The universe is not a puzzle with a solution. It is an infinite regression of puzzles, each one nested inside the previous one, each one stranger than the last. You are living through one iteration of this process, one moment in the long history of humans looking up and asking why. 2,000 years ago, humans looked up and saw wandering stars. Planets. They asked why planets move differently than fixed stars. Why Mercury and Venus stay close to the Sun? Why Mars sometimes moves backward? They invented epicycles, circles moving on circles, a complex mathematical model that predicted planetary positions with reasonable accuracy. It was wrong, completely wrong. But it was less wrong than saying the gods move planets according to whims. 500 years ago, Copernicus looked at the same planets, asked the same questions, found a simpler model. Sun at the center, planets orbiting in circles. Still wrong, but less wrong than epicycles. 400 years ago, Kepler refined the model. Ellipses instead of circles. 3 laws of planetary motion. More accurate, more predictive. Still wrong, but less wrong than circles. 300 years ago, Newton explained why. Gravity, universal gravitation. Every mass attracts every other mass. The planets orbit because the sun's gravity holds them. Less wrong, but still wrong. Mercury's orbit did not fit perfectly. 100 years ago, Einstein explained Mercury. Curved spacetime. General relativity, gravity as geometry, more accurate than Newton, more predictive, more mathematically beautiful, less wrong. But still wrong. Dark matter does not fit, dark energy does not fit. Quantum mechanics and general relativity contradict each other. Today, we are building the next model, trying to explain dark matter, trying to explain the Webb galaxies, trying to unify gravity with quantum mechanics. We will succeed. We will build a model that is less wrong than Einstein, more accurate, more predictive, more mathematically beautiful. And it will still be wrong. Because that is the nature of science, asymptotic approach to truth, getting closer without ever arriving. But each iteration teaches us something real about the universe. Something that does not change when the models are revised. Planets orbit the sun. That is real. The specifics of the orbits are complicated, involve perturbations from other planets, involve general relativity corrections. But the basic fact remains. Planets orbit the sun, galaxies form through gravitational collapse. That is real. The specifics are complicated. Involve dark matter, involve feedback, involve processes we do not fully understand. But the basic fact remains. Gravity pulls matter together, structure forms. The Webb galaxies do not invalidate this. They complicate it. show that our understanding of the specifics is incomplete. But the fundamental process is still gravitational collapse. Still dark matter halos. Still gas cooling and forming stars. We are not starting from zero. We are refining, correcting, improving, building on what came before. This is why science is cumulative. Why Newton's work still matters even though Einstein superseded it. Why Einstein's work will still matter when the next theory supersedes it. Because each theory captures something real, something true about the universe, even if it is not the complete truth, even if it is just an approximation valid in certain regimes. Newton's gravity is an approximation of Einstein's gravity, valid at low speeds and weak fields. Einstein's gravity will be an approximation of quantum gravity, valid at low energies and large distances. The Webb galaxies are telling us we need a better approximation, a more accurate model, a deeper understanding, and we will find it, because humans are relentless, curious, unwilling to accept mystery as final. We send Webb into space specifically to find surprises, to observe the early universe, to test our models, to discover what we do not know, and Webb delivered. Showed us impossible galaxies, broke our models, forced us to think harder. This is not a failure. This is success. This is exactly what we hoped for. Because a telescope that confirms everything we already believe is useless. It teaches us nothing, adds no new knowledge. But a telescope that reveals impossibilities, that shows us we are wrong, that forces us to rebuild our theories, that is worth every dollar, every hour of engineering, every risk. The Webb galaxies are a gift, a challenge, a call to think deeper, to question harder, to build better theories. And cosmologists are answering that call. Right now, in universities and institutes around the world, running simulations, analyzing data, writing papers, testing hypotheses. This is how science is supposed to work. Not smoothly, not predictably, chaotically. Driven by surprise, by anomaly, by the universe refusing to fit into the boxes we built for it. You are watching this happen in real time. Watching science at the bleeding edge. Watching the moment of confusion before clarity. The moment of darkness before dawn. This moment is rare. Most of the time, science is incremental. Small improvements, minor refinements, adding decimal places to known constants. But occasionally, rarely, something breaks. Some observation forces a revolution, forces us to rebuild from foundations. This is one of those moments you will tell your grandchildren about this. About the time the Webb telescope found impossible galaxies. About the time cosmology was rewritten. About the time we discovered dark matter is not what we thought. And your grandchildren will learn about it in school, will read about it in history books, will see it as an obvious step in the progression of knowledge. But you are living through it now, experiencing the confusion, the uncertainty, the thrill of not knowing what comes next. This is what makes science beautiful. Not the answers, the questions, not the certainty, the search, not the destination, the journey through mystery toward understanding that never quite arrives. The universe is vast, dark, mostly empty, governed by laws we barely understand, filled with phenomena that violate our intuitions. And yet here you are, one conscious observer, one small collection of atoms organized in a pattern that allows thought. One temporary structure that can look at the night sky and ask why. You cannot visit the Webb galaxies. They are 13 billion light-years away. The light you see from them was emitted before Earth existed, before the Sun formed, before our galaxy took its current shape. You are seeing the past. Ancient light. Fossil photons that have been traveling through expanding space for most of cosmic history. Those galaxies are still there. Still spinning. Still forming stars. But you cannot see them as they are now. Cannot send a message. Cannot make contact. The speed of light is not just a speed limit, it is a barrier, a wall separating you from the rest of the universe. You can see, but you cannot touch, cannot speak, cannot reach across the cosmic distances. You are alone, isolated on a pale blue dot. Surrounded by galaxies you will never visit, stars you will never examine up close, worlds you will never walk on. This is the existential horror at the heart of cosmology. The universe is filled with wonders, and all of them are forever beyond your reach. But you can understand, you can measure, you can calculate. You can build models that predict what those distant galaxies are doing right now, even though you will never see the light from their present state. You can know the universe even if you cannot touch it, can comprehend its structure even if you cannot explore it physically. And that knowledge, that understanding, is humanity's greatest achievement. Greater than any technology, greater than any empire, greater than any work of art. Because understanding the universe is understanding where you came from, how you got here, what you are made of, why you exist. The atoms in your body were forged inside stars. Stars that died billions of years ago in galaxies far away. Those stars exploded, scattered their atoms across space. Those atoms drifted through the cosmic web, eventually reached the gas cloud that collapsed to form the sun and earth. You are stardust, literally. Every atom heavier than helium was created inside a star, was ejected during a supernova, traveled for millions or billions of years before ending up in you. You are not separate from the universe. You are the universe. A small part of it that happens to be conscious, that happens to be looking back at itself and asking questions. The Webb galaxies are your ancestors. Not biologically, cosmically. They created the heavy elements, seeded space with carbon and oxygen and nitrogen, made planets possible, made life possible, made you possible. Without those early galaxies forming stars and exploding as supernovae, you would not exist. The atoms that make up your body would not exist. Earth would be a ball of hydrogen and helium. No rocks, no oceans, no atmosphere, no life. You owe your existence to those impossible galaxies, to their impossibly high star formation rates, to their impossibly early appearance. They should not exist. But they do, and because they do, you do. That is the ultimate answer to the question, why did galaxies form early? So that you could be here, now. Asking that question, not because the universe cares about you, it does not. Not because you are special, you are not. But because the universe is what it is. The laws are what they are. The initial conditions were what they were. And all of that, the entire 13.8 billion year history, the expansion of space, the collapse of dark matter halos, the formation of stars, the explosion of supernovae, all of it led to this moment. You, here, now, reading these words, understanding that you do not understand. The Webb galaxies reveal that we are still wrong about cosmology, still missing pieces, still building scaffolding that will eventually collapse. But we are less wrong than we were, closer to truth than before. And we will keep getting closer, because that is what consciousness does. It observes, it questions, it builds models, it tests them against reality. It revises them when they fail. You are part of that process. By learning about the Webb galaxies, you participate in humanity's collective effort to understand the cosmos. You are not just reading about science, you are doing science. thinking scientifically, evaluating evidence, considering possibilities, accepting uncertainty. This is what it means to be scientifically literate in the 21st century. Not to memorize facts, but to understand process, to embrace complexity, to live comfortably with mystery. The impossible galaxies are impossible until they are not, until we find the mechanism, until we revise the theory, until we build a better model, and then they will become possible, ordinary, expected. And we will move on to the next impossibility, the next anomaly that does not fit, the next observation that breaks our models. This is the cycle. This is how knowledge grows. This is how humans progress from ignorance toward understanding. You are witnessing one turn of the cycle, one moment in the long history of discovery, one step in the eternal process of becoming less wrong about the universe. If you found value in this journey through cosmic impossibility, help others find it. Like this video. Subscribe to this channel, because every view tells the algorithm that people care about deep science, about real physics, about confronting mystery honestly. The universe does not care if you understand it. But you should care, because understanding is what makes you human. What separates consciousness from mere matter? What transforms atoms into observers? The Webb galaxies are impossible, but they exist, just like you.